Okay, almost time.
Hello, Professor. Quick question.
Yeah.
Will you be making Tuesday's lecture recording available soon?
Yesterday's lecture?
Yeah, for the one from Tuesday.
Okay, I thought I have sent it out. Let me go and check, okay, because
Yeah.
I have to do something. If I forgot to do that something, it will not be shared. Let me see. See, I don't like the search function in Outlook at all. When you do cloud recording, it doesn't give me something relevant. So yesterday's office hours, I did send it out. Today's video recording Tuesday, right? So I did send it out.
So no, I meant the one from 17th. Today's the
Well, today is
19th.
the 19th. When they say Zoom Cloud, I didn't hit anything. Strange, I don't have any recording from the 17th. Not that I can see in my email.
I guess within the hours, I missed the first half hour, so I was just curious if there were any information from the first half hour that might not
Oh,
be
okay.
on the,
I don't have
the
a
lecture notes.
recording of that. I don't know. When I check Zoom cloud recording, nothing shows up unless I check the wrong mailbox. Current folder, maybe I should check all folder. Okay, let me see if I have any. Maybe it's, this was the office hour last night. This is the office hour, I believe. Office hour, office hour. Office hour, must be this one. This looks like the one, right?
Yeah, it looks about right.
Yeah, I have too many emails from Zoom and sometimes I just forget. Why don't I do it after class so that I won't take up class hour doing this?
Yeah, I was just
Okay,
checking. Thank you.
just shoot me an email if I forget, okay? Because I have too many things to do. Okay, shoot me an email if I forget. I'll do it after class and share that recording with you. Okay, let's get started then. Today I'd like to talk about the continuation of numerical methods to solve Maxwell's equations. This is an important field because most of the time we use numerical methods to solve Maxwell's equations in the modern day because of the speed of the digital computing. And that field we give it a very special name, which is computational electromagnetics. Okay. And we talk about differential equations that we need to solve and then integral equation. And I did not talk about surface integral equations much, okay? But you can read up in the lecture notes, so there are plenty of time that you can read those things up. But what is important is that if you have an equation that's not solvable, you find a numerical method to solve it instead. Okay, let me get this straightened out. So like differential equation, an equation that is not solvable, for instance, will be looking something like this. If this equation is hard to solve, if this is arbitrary. If the wave number k square is usually omega square mu epsilon in the electromagnetics, and if the wave number is arbitrary, there is no closed form solution. However, you can always rewrite this equation into an operator form. You can think of this as an operator, and this is a function. So it can be written as LF equal to G, where G is this thing over there. F is the unknown in your differential operator, and L is a linear operator. Okay, L is a linear operator. And usually this equation will have a unique solution if boundary conditions are specified. Okay. However, you can also convert a differential equation into an integral equation quite easily by saying that I can rewrite this equation as k naught square Vr is equal to Qr plus k naught square minus k square R V of R. Okay, these two equations are the same. I don't know if you can see them. If you look at these two equations, they're actually the same equation rewritten in a very different way. But they're in fact the same equation. But because I write this equation this way, I can think of everything on the right-hand side being sources. Okay, so if I know how to solve this equation, for instance, if I know how to solve a very similar equation to the left-hand side, and I can find a closed form solution, then I can think of everything on the right-hand side being the sources, and then the phi of R would be just the convolution of the Green's function. Okay, the convolution of the Green's function with the source on the right-hand side. Because I have a minus sign, I need to put in this minus sign. The R prime, this is the first convolution for linear system theory. Okay, the P is over where the source is not equal to 0. And then I would have to do the same thing. Okay, G of R, R prime, K square minus K naught square phi of R for the second term, the R prime. Okay, this will be over certain volume, but this is not 0. So K square can be an inhomogeneity. Okay, K naught square outside. Okay, and you have a wave coming in. an incident field, for instance, and then you want to look for the scattering solution. You want to look for the scattering solution. You can see that this is just the convolution of the Green's function on the source term on the right-hand side. This might be some source term Q of R over here. Okay, when you convolve the Green's function with the source term, it gives you the incident field. And then the other terms are called the induced sources due to the inhomogeneity. And I can rewrite this equation so that this I can call phi incident, okay? And then I can rewrite this equation so that phi incident is equal to phi r minus this thing, okay, GRR prime, k square minus k naught square, phi of r prime, dr prime. So this is unknown. This is also an unknown. So you can call this to be an integral equation. Okay, this is an integral equation. So what I've effectively done is to derive a very simple integral equation where everything on the left-hand side of this equation is known. But this is not known because I haven't solved this problem yet. Okay, I haven't solved this problem, so phi is not known. And what is embedded in the integrand is also not known. So when the unknown is embedded in the integrand, we call that an integral equation. Okay, let me put this down here. Okay, any questions on a very simple integral equation? And this is usually called the kernel. The part where you have this part is usually called the kernel. I don't know how to point to it well, but this part is usually called the kernel. Okay, let me use. Okay, so the term kernel has been used by many people. So it's used by the computer scientists to mean the core of an operating system. Is used by the mathematician to imply that it is an important operator, part of an integral equation, and so on. And it's also used by mathematicians in other abstract way. It's an overused word, okay? But every time you see the word kernel, make sure that you know what people are referring to. Any question on the integral equation? So, but what is important is that both integral and differential equation can be written as an equation of such a form, where this is unknown, this is known. Okay, if you look at your differential equation, it's also of that form. This is not known, this is the operator, this is known. Right-hand side is known, you know what the source is. So the idea is to convert this into a matrix equation. As I said before, the way to convert that is to let f be expanded as a sum of basis functions. You plug it in there, you will substitute this in here. I exchange the summation and the integration and the operator sign. So I would have ANL Fn equal to G. Can everybody follow that? I just substitute the summation into the above, exchange the L operator, which is the linear operator. You assume that this is linear. Exchange the order of summations in the operator, I get this equation. Can everybody get that?
Yeah, that's clear.
Okay, good. So I haven't had a matrix equation yet. The idea about computational electromagnetics, computational EM, okay, is to convert this into a matrix equation. So what you do then is to multiply this with a function Wm of R, okay? And then integrate. Okay, integrate, and then you choose different m's. M can be 1, 2, 3, to n of them. So if you do that, then the equation that you have will look something like this. Wm L Fn, n is equal to 1 to n, equal to Wm G, where m is equal to 1 to n, where this inner product is the same inner product that you have learned in reciprocity theorem, is just defined to be dr prime, Wmr prime G of r prime, just a volume integral, okay? So because of that, this will be a number. This will become just a number after the integration. This is also a number, okay? So the above equation can be written as a number, which I call Lmn. Let me not use script L. The number Lmn, let me call this number Lmn. The number that depends on the two indices m and n times an. N is equal to 1 to n. And then the right-hand side is also a number. And let me call that number G sub m. Now I have a square matrix system. If I choose n testing function, this is called a weighting function or a testing function. Okay, this is called a weight function or test function. Okay, if I choose m of them, then I will have m equation or n equation to solve. Then I will have a square matrix system. This can be put as a matrix system if I stack them up in terms of vectors, and then I have a square matrix to solve, where L is n by n, okay? Any questions regarding how we should construct the matrix equation for from a linear operator equation? Any questions so far?
I have a question on how does this reciprocity theorem jumps in?
Okay, reciprocity theorem has not been invoked yet, okay? Because the L operator is quite general. And I think we have previously related to the fact that reciprocity theorem is related to symmetry of an operator. What you find is that whenever you solve a problem that's reciprocal, and if you use the same testing function as your expansion function, if you choose n, Wm, and Fn to be the same, if L is a symmetric operator, this will become a symmetric matrix. I'm not going to prove that here, but you can do that as a homework. When L is a symmetric operator, the matrix element Lmn is symmetric in the sense that Lmn will be equal to Lmn if symmetric. Okay, and if it's symmetric, that means that the system is reciprocal. But I'm not going to go into that detail. You can prove to yourself that whenever you have a reciprocal problem, the matrix L becomes symmetric if you choose Wm and F sub n to be the same. And different names are used for this method. When these are finite element, these are called the finite element method. Okay. And when you use this for surface integral equation or integral equation, it's usually called a method of moments, but essentially they are the same method applied to differential equation and integral equation. So method of moments is called, when you use this for integral equation, finite element method is used, or the name being used, if you use this to solve differential equations, okay? But the next thing I like to introduce is the concept of function being a vector. If you have a function in one dimension, if you plot it out as a function of x, it will resemble something like this, okay? We should think of a function as a vector because now if I sample this function discretely, like what you would do in signal processing, Okay, it will look something like this. If you do, I didn't draw a very nice diagram, but if you do it very well, this sample points can be a good representation of the function. Moreover, if you are very good in interpolation, you can use this point that you have stored in the computer to interpolate for the original function everywhere. Okay, you can keep storing this value, and every time you need this function, you just interpolate for its value in between. That is actually how computer science works. Say if you call a function like a sine of x or cosine of x a Bessel function, or whatever you call in MATLAB, they actually have stored those functions in this manner at sample points. And if you need some value in between, the computer program just interpolates for the points in between, okay? So functions are stored in the computer in this manner in the discrete fashion. And you can think of this discrete storage as being a vector. If I were to display a column vector f, if this is the vector f, and if I were to display it to you, I will plot something like this. So a vector inside the computer and the functions are very similar to each other. Okay, and I like you to think of a function as being a vector, and you can generalize this concept to two-dimensional functions. Okay, and then you can say this is f of rho, and then if you were to sample it could be f of rho sub I, and you can generalize this to 3 dimensions, f of r, and you can sample it f of ri is let me put it this way. You can associate an index with the sampled value at location I. Okay, and I can also call this f of I. So once you store things in the computer, they only have one index instead of 2 indices. For instance, here on the right-hand side, I might have 3 indices, xi, yi, zi. Okay, but when you store in the computer, for every point in coordinate space on the right-hand side is one storage data point in the computer. So it will be stored in this manner, and to the computer guy, or to the guy who writes the computer, this is also a vector. So you can think of a 2D function, a 1D function, and a 3D function, all in terms of vectors when you have to store them inside the computer. Are there any questions as to how to think of functions as vectors? Any problem with that? It's kind of an abstract thing. Most students cannot grasp this. How can a 2D function and a 3D function becomes a vector inside a computer? Okay, so you have to think computer scientist if you want to think this way. And this is how mathematicians think. So if I have a function, it's a vector. Okay, and I can actually do basis functions expansion and convert it into a column vector. Like what they have done here is that when they expand the function f in terms of the summations of basis functions, I'm doing something like this. This is called triangular function. I'm using triangular functions to approximate this function into a piecewise constant approximation. And you can do this for any functions, and you can do it in 2 dimensions. In 2 dimensions, you will have to interpolate these functions using a pyramid functions like this or like this or like that. And you can also do this in 3D, and 3D will be tetrahedron. Okay, so these are called triangle function. And the French call it the chapeau function. Let me see if I know to spell chapeau correctly. Chapeau means hat in French. So this is 1D. 2D, this is called a pyramid. Okay, I don't know what you call it, but yeah, some kind of a pyramid. Okay, and in 3D, you have a tetrahedron. So how do you draw a tetrahedron? The tetrahedron is something that looks like this. Okay, so you will give a function value at 3 points, and you can think of this tetrahedron being able to interpolate a 3D function to points that are in between this vertices, 1, 2, 3, 4. Yeah, the tetrahedron has 4 vertices because that's why it's called a tetrahedron. And you can approximate 2D, 3D, and 1D functions all using these approximate methods, and hence convert a operator equation in 1D, 2D, or 3D into a matrix equation. Okay, this is an example of what happens in the 3D aircraft modeling, where you have this volume over here. You start to use tetrahedron to approximate the field outside. And then on the surface of the aircraft, you have surface currents. And you can approximate those surface currents with surface unknowns, where you can actually use perimeter functions or some more professionally known functions called the Rao-Wilton and Gleason basis functions and so on. But the thing is that given any surface, no matter how complex it is, those surfaces can be written as unions of triangles. And then you can define an interpolation function for every triangle. Those interpolation functions can be called the Rao-Wilton and Gleason function in computational electromagnetics. You call it Rao-Wilton Gleason. Okay. Basis functions. Okay. So any questions on what we have done? Essentially, given an operator equation, LF equal to G, we go through a method of moments, we go to a finite element method, we go to all these methods, and we convert this into a matrix equation. Okay, and what we have done in essence is that we have originally a problem which is in the infinite dimensional space, which is called a Hilbert space. By using this approximate method, okay, we approximate the function in the finite size space, a linear vector space, which is also called a Hilbert space. But when it's finite dimensional, we just call it a linear vector space. Okay, so we have converted a function which has been described or living in an infinite dimensional space into one that is been approximated in a smaller space, a finite dimensional subspace. So this method of converting from a linear equation in an infinite dimensional space to a matrix equation in a finite dimensional space, this is, what does it want to do this for me? Okay, so this is n by n. This matrix is n by n. It's definitely finite dimensional. This is n by 1. This is n by 1 vector. So this is called a subspace projection method. Where you have operators in the Hilbert space. Okay, and you project them into a smaller subspace in order to solve those equations. Any questions so far?
Yes, I have a question on.
Okay, sure.
So what does happen with accuracy of discretization first and solution of both integral and differential equations when we have singularities of the shape, like you see this long object on the left, and at the ends, you definitely will not be able to discretize properly the object, the singularity of this object?
Yeah, that is a very good question. Those are very good questions. And what people do then is that the current here is rapidly varying. So when you have a rapidly varying current, you need more basis functions to approximate the current. And the process that is done in the literature or in the community now is to do subgrading. You keep making the grid finer and finer. Instead of using the same coarsity of the coarseness of the grid, you make the grids finer. Or if you feel that the current here is more singular, you just increase the number of mesh points that you need to to solve the problem. So you will essentially make this equation thicker. if you have more and more unknowns. That means that you will solve this equation or this problem with increasingly larger number of unknowns in order to obtain the kind of accuracy that you want. So this matrix L can grow to be very large when you want higher and higher accuracy solutions. Does that answer your question?
Yeah, that makes sense.
Okay, there are a lot of art, a lot of detailed art on how to find this L, because I never talk about the detail. Okay, the detail will probably need another course. That is, if you want to perform this integration to find this matrix element, this is just LMN. Okay, and you actually have to perform the numerical integrations very carefully when L is a singular operator, like if you have a Green's function buried in here. It could be highly singular, especially if it's a dyadic Green's function, it can be highly singular. You have to do this numerical integration very carefully in order to find these matrix elements. Okay, so those are the fine points, but the big concepts are here. The big concept is that given the linear operator equation, you convert it into a matrix equation. Let's assume that you know how to do this and you have enough patience to do it. And you can go home and do all this integral yourself without getting bored. Okay, and that we have this matrix equation. What do we do with them? Well, we have to solve them. Okay, so the next thing I like to talk about is solving matrix equation by optimization. Okay, so this matrix system can be huge, and it can be matrix system involving billions of unknowns. Matrix system with billions of unknowns. So it could be that L F equal to G, n by n is very big. Okay, this is n by 1. This is n by 1. N can be 10 to the 9. Okay, or even bigger. And because of the digital computer that we have now, people are seeking larger and larger problems to have fidelity and accuracy. If you want high fidelity simulation, if you want high accuracy simulation, n becomes very large. Okay, n becomes really large. And how do we solve this problem? So instead of solving the problem directly by matrix inversion, which is very expensive, if you were to find L inverse, and you say if you see B is L inverse and this is n by n, the computational cost is proportional to n to the power of 3. So if n is a billion, n to the power of 3 would be proportional to 10 to the 27. This is the number of floating point operation, CPU floating point operation. Okay, this is usually considered as flop. Okay, how many flops do you need? And then the speed of a computer is usually measured in terms of flops, floating point operations per second. And then usually people don't talk about flops now, people talk about mega flops because computers are getting so fast. And then people talk about gigaflops. And now it's probably octaflops. I lost track. Okay, after giga, hexa, and computers are getting so fast that this name at the beginning there keep changing. Okay, but no matter how big the computer is, it doesn't whet the appetite of engineers. Engineers just want to solve bigger and bigger problems. And they want faster and faster computers. But given the computer resource that we have, how do we solve this problem efficiently? The rule of the game is to actually cast this into an optimization problem instead of solving this as a matrix inversion problem, because matrix inversion is not possible when you have to invert something. You want to keep the computer cost to be proportional to order n, okay? if you can get the CPU time to be proportional to order n instead of order n cubed, you can save a lot of computer time. You can have the number of floating point operations dropping from here to there. Okay, so let's see how we can do that. Well, we can cast this into an optimization problem, then it solves almost half of our problem, okay? Of course, if you have a quantum computer, that's even better, but we don't have a good quantum computer yet, given that we have insatiable appetite for computation. So I'm sure that all of you have been addicted to fast computer because you carry a cell phone around. A cell phone actually has about how many? 6 billion transistors. In the cell phone now. Maybe even more. I might not be able to keep track with this figure. So we are actually, each of us carrying a huge supercomputer around. Okay. So the key is to cast this into an optimization problem instead of a direct matrix inversion problem where it takes a lot of computer time. So if I have a problem like in one dimension, if I have this problem to solve, if I instead cast the problem of solving a x is equal to g, if I have this problem to solve, it's extremely simple. Okay, you don't need the computer to solve this. Even a little kid knows how to solve that. But if I were to cast this into an optimization problem, I find the optimal solution of this I of x. Okay, so then I say that I differentiate with respect to x, I get 2x minus 2g, and I want to set it to 0 to find the optimum point. And then I will get x is equal to g as well. So instead of having to do any other computation, I do the very deadening mechanical method of finding the optimal point. So let me cast all this problem into finding the optimal point. Let me say that if I, yes, somebody wants to say something?
You assume here that you have only one optimal solution, right?
Right, right, right. Okay, let me discuss that and please remind me to discuss that. Okay, so if I want to solve this equation LF equal to G, I want to claim that if I define the function L, which is given by this thing, and is given by 2F transpose dot G. Okay, this is a scalar number. This is just inner products between vectors. These vectors can be a billion numbers long. Okay, this can be n by n. Okay, this is the abstract version of this equation. This equation is 1D, but my f now is n by 1. Okay, so this is n dimensional. So I'm writing, instead of a functional in 1D space, I'm writing a functional in an n-dimensional space. And let me make life a little bit simpler. And I only write this function for a symmetric system. So I'm only considering the system where LT is equal to L. If L is not symmetric, there are other ways of finding this cost function. So what happens here is that if this is a function now, a function of a function is called a functional. This scalar is also called a functional. Okay. And if I can find the optimal point of this functional, which is a scalar number, then I can find the optimal solution without having to invert the matrix. Let me show you the fact that if I were to take the first variation of this functional with respect to f. That is, if I were to let f be equal to the optimal point plus a deviation from the optimal point. And we plug this in there and collect the first order variation. I don't know if you can do variational calculus in your mind, but if I were to do variational calculus, I will get two terms from the first matrix system. Okay. I'll get two terms because this is quadratic. I'll get two terms from the thing. And then from the second one, I'll get 2 delta f t dot g. Is everybody okay with this, or you want me to go into detail as to how I get the first variation? It's almost like calculus, but it's the multi-dimensional calculus. Is this okay with everybody?
Do you
Or you want
mind?
me to show more details? Hello, more details or is this step okay?
Can you go in more detail, please?
Okay, good. I'll show you more detail. Okay, let me plug this into this and collect terms. Let me take a new slide to show you more detail. Okay, so I have a function now which is consisting of multi-dimensional functions. Okay, minus 2 f transpose dot g. Just remember that these are vectors which are extremely long. Let me just let my vector f to be consistent of this. F plus a perturbation. I plug that in, I will get f0 plus delta f transpose dot L. L is a constant. And then I have f0. These are all vectors. Okay. In this course, I denote vectors by an over bar. Okay. And let me not worry about the second term. The second term is quite easy to deal with. Actually, I can just write it down as well. Okay, then I do the simple things that I would do in linear algebra. These are vectors and matrices. I multiply them out, I will have 4 terms here, right? I will have 4 terms here. I will have a term that is f0 transpose dot L dot f0. That is a leading order term. I would have a term that comes from this dot L dot f0. Okay, can you see that term? This term multiply this term gives me that. And then I have another term that is this term multiplied by this term times a small term. Okay, f0 transpose dot L dot delta f. And then I have the last term, 4 terms, right? Altogether 4 terms. Delta f L, this is transpose dot delta f. Can you see all these 4 terms? Can you see them?
Yes.
Okay, delta f is supposed to be small. Okay, so this is proportional to the square, the product of delta f. It is going to be very, very small. This term is going to be the biggest. And so I is going to be expanded as such. And I can think of I as I0 plus delta I. And I can call this leading term I0. And then the rest, the linear term, I call delta I. So I get delta I equals to what I have written down in the previous slide. Okay. These 2 terms, which is essentially these 2 terms. And then if I take the leading order terms of this, I forgot 1 term over there, sorry. There should be 2 terms coming up from the last term. There should be, from the last term, I never did anything, okay? It should have 2 terms, 2f0 transpose dot g minus 2 delta f transpose dot g. I should have these 2 terms to write down in the last term. So I will call this term and this term, which are not small, I0. Okay, this is I0. This will be put together with I0. And then the other terms that are proportional to just delta f would be this term delta F transpose dot L dot F0 plus F0 transpose dot L dot delta F, and then plus this last term. Okay, can you see that? So the first order variation is just this one. Okay. Can you see? Okay, now that I have derived this, I want to say that these two terms are the same because I have a symmetric matrix. If you take the transpose of this system over here, you get this system, right? If you know how to take the transpose of product of matrices, you take the transpose of this, you get this. So these two are the same. So they are the same. That means that I have an equation that's actually 2 delta F T minus L dot F0 minus 2 delta F T dot G. And if I'm at the optimum point, if I'm at the stationary point, just like this simple problem here, this delta I should be 0. Okay, and if delta I is equal to 0, if delta Ft is arbitrary, when I take this delta F, I take the delta F in an arbitrary direction, then this two can only be equal to 0 if this equals that. Okay, so what I have essentially proved to you is that the optimal solution is given by L dot F0 equal to G. Okay, so one way of solving this equation for the optimal solution is by finding the optimal point of the cost functional. And if you can find the optimal point of the cost functional, you essentially have found the solution to this equation, LF not equal to G. Okay, so instead of inverting the matrix, which is very expensive to do, I write the cost functional, find where the point that is optimal is, and that solution I call F sub 0. F sub 0 actually would solve this equation. Okay, so does everybody catch this idea? Any questions on this idea? Anybody? So if no question on this idea, let me move on then. Then this is actually a very hot area of research, optimization, machine learning, and all these things you read up about AI now. Essentially, this is a 2D version of that. You have the cost function. You try to find where this optimal point is. You do gradient search method, steepest descent method, conjugate gradient method. There are potpourris of methods in the literature that allows you that if you start with an initial guess, you arrive at the optimal point. I will not go into the detail, but I wrote this up in the lecture notes. What you need to do is that at any point, you need to find the gradient of your search, and you search along the gradient direction until you find the optimal point. Sometimes you're not lucky, you will zigzag along and you cannot find the optimal point. Sometimes you're very lucky, you find a path where you zoom into the optimal point very easily. And I will not delve into the details. And the details are written up in the lecture notes. And if you have done machine learning or any other things, you will have encountered this kind of problems before too. Okay, is this fair enough? Or are there any questions?
I still have question on the uniqueness of this minimum of optimization.
Okay, yeah, I forgot to mention that point. Okay, you can prove that if a problem is quadratic, like this problem over here, this is called a quadratic function in one dimension. If a function is quadratic, it only has one optimal point. Okay, so what is the equivalence or the analog of a quadratic functional in one dimension? In multi-dimension, this is an n-dimensional space functional. This is called a quadratic functional. Okay, because you have something like f times L times f is proportional to the square of f. So it's the n-dimensional or analog of this quadratic function. You can prove by mathematics that it only has one optimal point. Okay. Unless L is not linear. If L depends on F, which is actually the case when you do machine learning and so on, L is not simple. But for computational electromagnetics, L does not depend on the solution F unless it's a nonlinear electromagnetics problem. Then the solution is unique. Okay. If L is a simple linear problem, the solution is unique and the problem is linear. Okay.
Yeah, that makes sense because
okay, good.
my initial
So
question
I hope
was what if non-linear and we have many minima or maxima.
right. If it's non-linear, I hope your professors will only give you linear problems to solve. But unfortunately, our world is full of lots of non-linear problems. So you will have to scratch your head to figure out where to find the minima of those things. Okay. I'd like to move on to talk about the finite difference method. It is one of the most popular methods in computational electromagnetics, and especially the one called the Yi algorithm, started by Ken Yi. Okay, so it's actually a very simple method. Given Maxwell's equations, how can I solve it approximately? I have a huge computer available to me. So the thing is that why don't I just find finite difference approximations of whatever I have and see if I can solve those equations using finite difference. And there are three kinds of finite difference. One is called the forward differencing. And essentially when you find the derivative, you're essentially finding the slope of the function. You can approximate the slope using the value at this point, subtracting the value of that point and divided by the separation. This gives you the approximate slope, and this is called the forward difference. And you can do it backward and take a point behind it, and then you can find this approximate slope. And then you can do a central difference where you take a point ahead of itself, a point behind itself, and then use that to approximate the slope. And intuitively, you can see that the third method is the best method because it gives you the closest value to the slope compared to the other two. And you can actually prove algebraically by Taylor series expansion that this method is in fact the best. Okay, but I'm not going to go through that proof, but hopefully by just looking at the picture, you can see that you in fact have a method that is very easy to implement and accurate. So the idea of finite difference method is that whenever you have a derivative with respect to time, you can always approximate it with a difference value. Okay, it can be like this. Okay, this is forward difference, backward difference, and finite difference. But then if you have a say a wave equation to solve, like partial phi, let me not use phi, maybe, yeah, phi is good enough. So if I have a wave equation to solve, okay, this is a wave equation to solve. And the field is both a function of space and time. Then what they can do then is to find a finite difference approximation of this second derivative. And I know that if I have first derivative, I know how to use central differencing to find the first derivative. I would do the value of this function at t plus delta t over 2, subtract the value of this function at t minus delta t over 2, and then divide that by the time step. Okay, then this is called a central difference approximation. And I can do it 2 times. If I have second derivatives in time, okay, I do it 2 times, and then you will have, I don't know if I need to go through this, but you will have let me just write it here. Okay, if I do it 2 times, I will have to do this one more, and then apply the central differencing formula one more time to each of this term. And then what I have done is that the central difference is approximated as phi of r t plus delta t minus 2 phi of r t minus plus phi of r t minus delta t over delta t squared. Okay, if you go to the algebra, that is what you have. Okay, and in the finite difference literature, the central difference approximation is preferred because it's second order accurate. Which means that the error will be proportional to the time squared, the time step squared. Since delta t is a small number, the square of it is even going to be smaller. So we always try to use central difference approximation if we could. And from this picture pictorially, you can see that the central difference approximation is the best one. Okay, and also people like to use this notation that instead of writing this as the argument of t, it's usually preferred to say that t is equal to L delta t, where you use the delta t as the clock, okay? And then this is usually just written as phi L. Okay, and then if you have t plus delta t, then you just write this as phi L plus 1, a lot easier to write. And then you can say that then this second order derivative written with this difference notation can be written as phi r. Let me write it this way. L plus 1r minus 2 phi lr. Okay, where the exponent L now denotes the time. And this is phi L minus 1 r over delta t squared. Okay, is this fair? This is just a simplicity of notation in the finite difference world. So the great thing about this is that with this, if I plug this approximation to the right-hand side of this equation, I can do something called time marching. Okay, if I just do something like this, then if I plug this into the other side, you can actually show that I can move this to the right-hand side and then I keep the rest on the left-hand side. So I'm going to substitute this in and move terms around. I hope you can follow that. And then what happens is that you will have delta t squared Laplacian of phi r L, let me just call TL instead of phi RT. And then on the other side, I will have these other terms, but I'm going to move some of these terms to the other side. Okay, I'm going to have phi LR minus phi L minus 1R. Okay, and then on the right-hand side, I'm going to have just phi LR. So I have effectively used this approximation, plug into this original wave equation. But this wave equation now has a very interesting meaning. It says that this is future time or future time step. This is the previous time step. And this is the present time step. And these are also at present time steps. So what it says is that if I have knowledge of the field at the previous time step, the present time step, and its derivative at the present time step, I can use that to predict what the field would be like in the future time step. This is called time marching. So if you keep repeating this process, that if you start with some initial value in time, and then keep repeating this over and over again, you essentially would be able to fill the solution up, like if this is time and this is R, I cannot draw in 3 dimensions, okay? You will have the field values as a function of R. And you can essentially march in time, use this process, march in time, and fill out the value of this function for all time. Okay, for all time. This is called time marching. Okay, time marching or time stepping. Some people will call it time stepping. So, Eddie, are there any questions regarding this concept? This concept is rather simple. Convert a partial differential equation in time into a time marching equation or time stepping equation using finite difference approximation for the time. Any questions on this?
Yes. How do we fit initial conditions into this equation?
Well, initial condition, it turns out that, well, you actually have to have 2 of them at the present time and the previous time. So you need 2 conditions to march forward. So if you only have 1 condition, that's not enough for you to do time marching. Well, why do we need 2 of them? Well, there's a very simple explanation. This is a second order equation in time. It involves a second derivative in time. So if you have studied initial value problems, if it is the second order differential equation in time, you need 2 initial values. You need both the field value and its derivative. Okay, those are called Cauchy data in the mathematics language. And so you have to have 2 values. Instead of having the field value and its slope, you can have the field value at 2 previous time steps. That is sufficient for you to march forward. Okay, so instead of having Cauchy data, you can have just 2 of them. Okay, does this make sense?
Yeah, that makes sense.
Okay, good. So this is the time marching or time stepping method, which I've just talked about. Okay, and you can use that to fill up the solution in all space and time. And then the question that you have to ask yourself is, you still have to approximate this equation on the left-hand side. You have this Laplacian that you need to approximate. What you can do is actually break space. So if I were to draw in 2D, then you also break space into points so that you can use finite difference approximation to approximate this Laplacian operator as well in the x and y direction. So if I were to draw the 3D picture, okay, this is x and y, and then this is t. So you start with some initial value of the field in the xy plane. This is just a 2D problem, okay, 2D problem. 3D is harder to draw. And then you can imagine that if you know the field values at the xy plane at discrete point values, you can also evaluate the Laplacian using finite difference formula, finite difference in space. Then you can march the solution forward in time upward and fill up the whole solution space. Does this make sense to you? Does this make sense to you? So I'm not going to talk about the finite difference of space because it's quite straightforward, okay? It's quite straightforward. If you know how to do finite difference in time, you just apply the same method, you will get the finite difference in space, okay? But let me talk about stability analysis. This method is useless if the method is unstable. If you march forward in time, this formula is deceivingly simple. But what happens if the solution keeps growing bigger and bigger? Then this method is useless. We like to know when this method is good and when it's not good. So we have to do stability analysis, which is what I'm supposed to do next, okay? Stability analysis. So I'm going to do a very simple equation where I have, well, homogeneous medium. So I have this equation that I need to solve is equal to Laplacian. And then the Laplacian is going to be very simple. And I'm going to apply finite difference to the space as well. So if I were to apply finite difference to the space and do it in the x direction first, and if you don't mind me doing quickly, it will be second order finite difference method. And I'm going to use this notation that I'm going to use three indices to denote x, y, and z. So the x will be denoted with m, the y will be denoted with n, and then the z will be denoted with p. And by the same token, I denote the time with superscript L. And then the second order derivative in space will be something looking like this, okay? I take the finite difference at the neighboring point, okay, minus that at the present point, plus that at the other neighboring point, one step in the opposite direction, divided by delta x squared. Okay, is this fair enough? Or you want more details? So second derivatives can be approximated as such. Is this fair, or you want more details?
It's clear.
It's fair, right? Very good. Excellent. So I'm going to check the stability of my method. I'm going to use a Fourier mode. I'm going to let the Fourier mode be propagating in this solution space. So I'm going to let my MMP L to be something proportional to motivated by something like, well, I'm going to use the other time dependence, e to the I kxx plus I kyy plus I kzz. I'm going to be motivated by using this Fourier mode as a test solution for my finite difference method to check if it's stable, okay? And if I were to write this Fourier mode in terms of finite difference notation, t is LT, so this thing I can actually put in A0 here if you want to. So this Fourier mode can also be written as a to the power of L e to the I kx, let me see, kx m delta x plus I ky n delta y plus I kz p delta z. Can you see that? Okay. Essentially, in the finite difference world, I let t equal to LT, I let x equal to n delta x, I let y equal to n delta y, I let z be equal to p delta z. I plug it into the exponent, my Fourier mode becomes something like this in the finite difference world. Can everybody follow that? And then I'm going to plug this Fourier mode back in, okay? I hope you can see this. This is just that, okay? E to the minus I omega LT, L delta T is just A to the L, okay? It's just that. So I'm going to plug this in, and what I'm going to argue is that because you're shifting the function in the x direction by +1 and -1, and what you have is that by a very simple analysis, this is just the same as e to the I kx delta x minus 2 plus e to the minus I kx delta x, and then multiply by the same function again. Okay, can you see that? If I were to plug this in, the only change in these three functions is in the m index. The m index is going to shift this thing by a little bit, and each of them will bring out a small phase shift like this. And for the middle term, there's no change. Okay, can everybody follow that? Okay, if you can follow that, that's wonderful. And I can write this as -2 or +2 cosine kx delta x minus 1, okay, times phi m n p l. Okay, I'm going to get that. And then I can use trigonometric identity and write this as 4 sine square. This is kx, okay, it's not very good handwriting. Kx delta x. Kx delta x over 2 phi m n p l. Okay, can everybody see that? I just use some trigonometric identity and got this. Okay, so I need this for the stability analysis, because if I were to now plug this approximation for partial square, partial x square, partial square, partial y square, partial square, partial z square, the next equation that I'm going to get will look something like this. Well, on the left-hand side, I would have something like 1 over c partial square partial, sorry, this is t. Phi, okay. And let me write this as such, okay. P m n p, okay, would be equal to minus 4 delta s square times sine square kx delta s over 2 plus sine square ky delta s over 2. I'm going to assume that delta x to be delta y to be delta z, and all of them I call them delta s. Okay, so all of them will share the same discretization to simplify the analysis. Kz delta s over 2. Okay, and then I have phi m and p. Okay, and I have not done the finite difference in time yet. If I were to do the finite difference in time, the left-hand side would be approximated with something else. It would be like phi m and p l plus 1 minus 2 phi m and p l plus phi l m and p. Okay, this would be the left-hand side. Okay, left-hand side will become that. And then if I were to plug this Fourier modes into the left-hand side, where the Fourier mode consists of this AL, okay, consists of this AL, and the left-hand side will only affect AL because there's only term that has space, time dependence in it. So left-hand side, okay, will become 1 over c squared delta t squared, okay, and then the AL will show up, AL plus 1 minus 2AL plus AL minus 1 phi m and PL. This is the left-hand side, and then it should be equal to the right-hand side, okay, and I can actually now put an L on the right-hand side. Okay, everybody follows that. And I'm going to assume that because of the dependence of AL is actually dependent on omega in a special way. Okay. AL is dependence on frequency in this manner, and T is LT, L delta T, L times delta T. So when when I have this kind of relationship, I can say AL plus 1 is just G times AL, okay? Because the relationship is very simple, because my AL is actually A naught e to the minus I omega L delta T, okay? If my AL is of this fashion, which was what it was below before, then I have this very simple relationship. I call this G the amplification factor. This G has to be absolutely less than one's possibility. Otherwise, the program that you write will become unstable. So I plug this in here because my AL is of this form. So it allows for this kind of behavior, plug it in. And if I plug that in, then the left-hand side just becomes G, okay, G minus 2 plus G minus 1 times this factor, which is kind of rather complicated, okay? I can bring this factor to the right-hand side, and I have this thing over here. Well, let me call this thing is a very complicated function to write. Let me call it S squared. Sum of three signs, I call it S squared. And then what I have is that if I move everything to the right-hand side, I have this minus 4, and then I move this t squared delta c squared to the right-hand side. I will have something like 4 delta t squared, okay? Over delta s squared. This little s is different from this s. This is a big S, okay? This is a big S, and this is called big S. And then I'm going to have this equation because AL is going to cancel. If I plug this in, I have an AL on the left-hand side. I will have an AL on the right-hand side too. And then I have the other factors, they all cancel out. And the only equations I'm left with is this equation. Okay, this is the only equation I'm left with. And it's a second order algebraic equation in G. This is an equation in G squared, G and constant. Okay, if you look at this equation, there's an S here that got erased, okay? I can solve for my G, okay? I can solve for my G, I can call this factor R, and in the lecture notes, I call it R squared. So this is actually G minus 2 plus G minus 1 is equal to minus 4 R squared S squared, okay? That's the only equation I'm left to solve for. And G, remember, is my amplification factor. Okay, G is my amplification factor. And let me see how it behaves. I can solve for this equation for G, and it's a quadratic equation, and we know how to do that using high school algebra. If you do high school algebra, the equation, the solution you get is something looking like this. Okay, R squared S squared minus 1 over that 2. That 2 is just 1. Okay, so you can get this equation, and we know how to do this. And it turns out that well, we have better to have G less than 1 because it's an amplification factor. If it's larger than 1, the program will be unstable. It turns out that if you let RS is less than 1, this term becomes imaginary. And if it becomes pure imaginary, the amplitude of G, okay, will be obtained by squaring this term plus the square of that term. And you can show very easily that G will be 1 if RS is less than 1. Okay, I'm not going to show you the algebra because it's quite straightforward algebra, but you can do that at home. And if G is less than 1, then you will have a stable algorithm because G is the amplification factor. And you can go and think more about this, okay? So if S is the sum of 3 signs, okay, capital S is bounded by 3. So it would never be larger than 3, okay, which means that S, 1 over S, 1 over S is larger than 1 over root 3. Okay, if I take the square root of that equation and flip my inequality around, I have 1 over S is larger than 1 over square root of 3. But from this equation, it says that R is less than 1 over S. Okay, if you combine these two inequalities together, it says that if R is less than 1 over root 3, okay, then RS will be less than 1 by this inequality. Okay, you can think about it carefully. So this is a stability criterion. And let me track back as to what my R is. My R is this very complicated factor over there. Okay, so if you put that complicated factor back in, you find that the stability criterion is that the time step is less than the space step divided by the velocity times 1 over root 3. Okay, if you plug in the definition of R, R is defined to be, let me see if we can find it. R is actually delta T over delta SC. Okay, that is the definition of R. So that actually is very interesting. It says that you cannot do finite difference time domain with arbitrary time steps. It has to be bounded by the space steps. The smaller the space step is, the smaller the time step it has to be, okay, in order for stability to occur, okay? And I can write up more about the physical meaning of this in the lecture notes, but I won't go into detail at this point. But I like to also talk about the finite difference time domain method, which is invented by Kane E in about 1966 and has become vastly popular, and actually is popularized by Alan Taflock. He applies it to almost everything you could think of. Okay, so this method is very simple. You just put Maxwell's equations on the grid, and then you write finite difference approximation for the 6 Maxwell's equations, or 6 components of the Maxwell's equations. You have curl of E is minus dv dt. This is 3 Maxwell's equations there. Curl of H is equal to dv dt plus j. You can put all the components on the E grid. This is called a E grid. And then you can do time stepping with this E grid, and you can solve beautiful problems in electromagnetics. You can write a code in one afternoon if you're skillful enough. Okay, you're very good with coding, you're very good with mathematics. If you are very good with bookkeeping, if you take all your finite difference properly, you can do your finite difference time domain code in one afternoon. Here is just an example from math work, where you can actually march things forward in time. And here's another example of the FDTD simulation of MRI, magnetic resonance imaging core. Okay. There are also something on error analysis that I don't have time to cover, but it will be covered in the lecture note. I cover stability, I cover time marching, and of course, you don't have the liberty to choose your space step to be any size. You say that, well, if I choose my space step to be any size, okay, then my time step can be any size. That, of course, is not possible. Your space step has to be small enough to model the field, to capture the physics of the field properly. And that accuracy analysis is done in the lecture note. Okay. Any questions so far before I let you go? So this method is vastly popular, and if you are liking this method so much, you can spend one afternoon writing a code for it. Maybe you can write in 1D, then you write in 2D, and you write in 3D. And then you have a Maxwell's equation solver in one afternoon. Okay? I'll let you go if you don't have any more questions. And by the way, there will be no lecture next week. Next week is Thanksgiving, right?
Yep.
Hello? Anybody there still?
Yeah.
Okay, next week is Thanksgiving, but I have been giving you take-home exams that consume your times. So I'm allowed to give you 3 days off. I had given you 1 free day off during fall break. So I can give you another lecture off next week, and then you can enjoy your Thanksgiving more peacefully. Is that fair enough?
So there won't be any homework due next week, basically.
I will give one homework tomorrow, but it will be due the week after Thanksgiving.
Great.
Okay, so you enjoy your Thanksgiving and be careful when you're out there because COVID is rising. The pandemic is still raging up out there. And avoid gathering with big groups. Gather only with small group of people that you know. Or if possible, tested to be COVID negative. Okay? Okay, good.
Sounds good.
Okay, take good care of yourself.
Thank you, Professor.
Okay, you're welcome.